Well, this is a non-calculus based course. Finding the area under a curve is something that we don't have the skill set for unless we've taken calculus. And we don't need the skill set for finding the area under a curve such as this, because somebody has been very nice and done all of the work for us already and made this table. So we're going to get very familiar with this table we're going to call table A. This table will answer the percentile or proportion of observations falling below the curve. Remember, percentile is what percent of the observations are you greater than, or what percent of the observations fall less than the value that we're looking at. And that's what table A is going to do for us. It's going to be very, very beneficial. So the standard normal curve fits any data set in the world, whether we're talking about the test scores or the ages of the presidents or any normal distribution in the world, can be changed, converted, standardized to fit this table. Then we don't have to do all the work to find the area under the curve, because this table will do it for us. This has 2 pages to this table. Okay? It has positive, meaning, oh yeah, your z-score or your number of standard deviations was above the mean, or the negative values, meaning your score was below the mean. So if you have a z-score of 0, what does that mean? Oh, you're at the 50th percentile. You're right in the middle. Half of the people were better than you, half were worse than you, so to speak. So a z-score of 0 means you are the mean. How do we read this table? What if I had a z-score of 1.2? Positive 1.1, 1.12. So if my z-score is 1.12, let's say. Z-score is 1.12. So I go down to 1.1, I find 1.1, and then I go across to 0.02, and then I would go across 1.1 and then down at 0.02, kind of like using a multiplication table when we were younger. Oh, 0.8686. So if my z-score was 1.12, meaning I was 1.12 standard deviations above the mean, I would be at the 86.86 percentile. That's how we're going to use table A. And we'll do some more examples with it here in a moment. So standard normal distribution, or I'll talk a lot about the standard normal curve. All it does is convert any data set in the world to have a mean of 0 and a standard deviation of 1. So let's look at a couple examples. How are we going to use this? Okay. So how to find the areas of this normal curve. We just spoke about this in a minute, and here's some example from the text, or I should say a definition from the text. You're going to be required to draw this curve over and over and over again. You won't necessarily have to write mu and then mu plus 1, 2, 3, mu minus 1, 2, 3, but that's what we're doing for every single curve in the world. Okay, so you're going to draw a normal distribution and label your axes. You have no choice. You must do that. You must draw the curve, draw the x-axis, and label it with 1, 2, 3 standard deviations on either side of the mean. Okay, then what we're going to do is perform a calculation. Okay, we are going to standardize the value, meaning z-score. Z-score is a standardized value. So if we go back and look at the original data set from our test score of back early on, the one that we used over and over again, let me find that here. It had a mean of 35.44, and it had a standard deviation of 8.77. So 35.44, and then I would add 8.77 over and over again, 44.21, and I could keep going here. So the next one would be 52.98, and so on. And here I would do 35.44 minus 8.77, and I would keep going. Now, remember, we had a score of 43. Based off of the relative standing or the percentile, we were at the 80th percentile. Let's see if that data was actually normal or not, and how we would do this calculation using table A and the normal curve. So remember what a z-score is. Z equals your score that you're looking for minus the mean divided by the standard deviation. So let's grab our handy dandy calculator here again real quick, and let's do some calculations, because I don't really want to do all this work by hand, as you can tell from me struggling just adding and subtracting in my head. So we're going to clear out of here and go back to our main screen. And what is it that we want to find out? Well, we want to do 43 minus 35.44. And then we want to divide that by 8.77. Oh, so we have a z-score of 0.86. Okay. Z-score of 0.86. Now, I know what my z-score is. Let's go to my table A to try to figure out what my percentile is for 0.86. Remember when we looked at relative standing, it was around 80%. So if I have a z-score of 0.86, I know that it's positive. Therefore, my answer better be above 50%. 0.8, and then I come across here, 0.8, and then 0.6, and I come down and it's 0.8051. Yeah, approximately 80%. So how are we going to solve a problem for a normal distribution? We're going to standardize the data. When I did this z-score down here, what did I really do? I changed the mean into a 0, and I put it onto this curve. So really, it's all the same. My score of 43 would be right in here somewhere. So I would be trying to find the area to the left of the curve, under the curve. They'll talk about a lot. Find the area under the curve. In this case, the table A can only give us this area to the left. We'll look at an example in a minute on how to find the area to the right. But if we want the area to the left, the table A will give us that answer. So again, standardize your value. Take your original data and turn it into a z-score. Okay, what is a z-score? Trying to find out how many standard deviations are you away from the mean. Okay. All right, so we can also do this on our calculator. Let's clear out of finding our z-score. So our calculator can do all of this in one step, except it does even draw the picture, but you're going to be required to sketch the picture and shade the area in question. Okay? So we were trying to find the area or the percent less than 43. So in our calculator, we can go to second distribution. So blue second, and then vars, or second vars, which is distribution. And then we can go to normal CDF. Normal CDF is going to ask us to put in the lower bound, the upper bound, the mean, and the standard deviation. So for my lower bound, I want it to go forever. Well, forever is a concept the calculator can't understand. It doesn't understand infinity, but I want it to go all the way to negative infinity. So we're going to use -1 e to the 99th to represent negative infinity. So I want the area under the curve from negative infinity all the way up to my score, which was 43. Whoops. So how do we put in negative infinity? We don't want to use minus. We want to use the negative sign. -1 e 99. Don't put e to the power of 99, because then that's doing a power to a power. So my lower bound is -1 e to the 99th. My upper bound, I want to find the answer from negative infinity all the way up to 43. The calculator's like, sure, I can do that for you, but you need to tell me what the curve is. You need to give me the shape, and or not the shape, we know it's bell shaped, but you need to give me the important information. Remember, we describe every normal curve with the mean and standard deviation. So we tell it, oh, the mean was 35.44. And the standard deviation was 8.77. And then we tell it to paste and it will type it in. If you have an older calculator, you'll have to use parentheses and type it in this way. So you'll see normal CDF, lower bound, upper bound, mean, standard deviation. Hit enter and it does all the work for you, 0.8056. Well, that's pretty much what we found when we looked at table A. So what this calculator did was it took our original data, the mean of 35.44, the standard deviation of 8.77, and the score of 43. It did a z-score. It went to table A, it looked it up, and it spit the answer out for us. So remember, the calculator is very, very strong, but it doesn't have a brain. You have to be the brain. You have to tell the calculator what to do. But this is the same thing that we just did here using table A. Let me get rid of this calculator real quick, maybe. We just did on the by hand right here, as you can see again, and we did it on the calculator. Either way is fine for the AP test. But regardless of which way you do it, you must draw the curve, label the axis, and shade the area in question. To find area using table A, we just went through it. Here are the steps for the calculator. We go to normal CDF, lower bound, upper bound, mean, standard deviation, and the calculator will do all the work for you. Pretty slick. Let's take a look at an example here. Okay. Talks about Jordan Spieth hitting a golf ball a certain distance. It says that his distribution of drives is normal. Once we know the data is normal, we think automatically z-scores. Normal data, do z-scores. Normal means z. Okay. Normal distribution with a mean of 304. So on average, his average drive or his mean length of a drive was 304 yards, and he has a standard deviation of 8. Notice I use mu and sigma here because this is the population. This is for all of the drives that he's hit. So this is the mean of all his drives is 304 with a standard deviation of 8. The question says Jordan would need to hit a ball at least 290 yards to have a clear second shot that avoids the trees. What percent of his drives will travel at least 290? Okay, so we're trying to answer what percent of all of his drives would be at least or greater than 290. So we made the curve up here. Mean, 304, plus 1, plus 2, plus 3 standard deviations. Well, table A doesn't know about Jordan Spieth's driver. Table A can only answer the question for the standardized value or the standard normal distribution. So that's why z-scores are so important, because we don't have a table for Jordan Spieth's drive or for your test scores or for how tall somebody is. We don't have a table. We'd have to have millions of tables for every situation in the world. So instead, we can convert this data or standardize it to a z-score so that it matches table A. To do that, to standardize my scores, z equals my score minus the mean divided by the standard deviation. So I have negative 14 divided by 8, which, as you can see up here, is negative 1.75. Okay. I'm trying to find what percent of his drives are greater than. That's why this area has been shaded to the right, greater than. But table A can't do greater than. Table A only finds less than. Now I know I'm looking for what proportion of all scores are greater than negative 1.75. So what have I really done here? I've converted this z-score down here. I've converted Jordan's data on this graph to match 0, 1, 2, 3. Negative 1, negative 2, negative 3. So it's the same picture, but I have changed the mean and the standard deviations. Once I've done this z-score here, then I have changed this problem from the probability that x is greater than 290. I've changed that to the proportion or probability that z is greater than negative 1.75. It's the same exact question. Now, grabbing table A, I'm going to look up negative 1.75. Negative 1.75. So I go negative 1.7. I go across here to 5. Oh, 0.0401. But remember that the table can only give us the area to the left. So negative 0.0401. So this little bitty area right here is 0.0401. But that's not the question. It's not what percent of his drives are less than 290. It's what percent of his drives are greater than 290. So if 4% of his drives are less than 290, that would mean that approximately 96% of his drives would be greater than 290 or 0.9599 or approximately 96%. Because remember, the table A only gives us the area less than to the left of the point in question. Okay. How would we do Jordan's problem on the calculator? Okay. Well, once again, it's a normal CDF problem. So clear this here. Remember, we find normal CDF by going to distribution, which is second vars, normal CDF. Now, I don't want to go to find the answer all the way to negative infinity. My lower bound was 290. My upper bound, now I want to go all the way to positive infinity. So I'm going to do 1E99, which is our way of telling the calculator to go to positive infinity. And then I'm going to type in how to describe the distribution of Jordan's drives. Remember, we always describe a distribution with mean and standard deviation. So the mean was 290 and the standard deviation was 8. And then I let the calculator do all the heavy lifting for me. Wait a minute, I messed up. Okay, so I put in 290 for the mean, but the mean of Jordan's drives was not 290. All right, so lower bound, 290. Upper bound, positive infinity. Mean, 304. Standard deviation of 8. 0.9599. So it's just another way to use table A. But again, whether you use the calculator or you use table A and do the z-score calculations by hand, you must draw this picture. We must have the curve and the area shaded. Since we've already done the work for Z here, we can check to see that this really is the same thing. Normal CDF. Now, I want the lower bound to be negative 1.75. But I didn't get my decimal point in there. So negative, again, don't use the minus sign, use the negative sign. 1.75 all the way to positive infinity. But now since it's standardized, the mean is 0 and the standard deviation is 1. Paste and hit enter. 0.95994088. Same exact answer. So you can see what we're doing here. That by standardizing it will give us the same answer as using the raw data. What if I wanted to know the probability that his drive Let's say that he hits a drive less than 296 yards. So he hits anywhere from 0 to 296. I can see here that 296 is one standard deviation below the mean. By the 68, 95, 99.7 rule, I know that 68% of the data falls in here. Therefore, these two tails out here must equally share 32%. So that would tell me that in here is half of 32%, or approximately 16% would be less than. Well, how would we do that on table A without using the 68, 95, 99.7 rule? Well, to use table A, we must standardize the scores, which means change them to z-scores. So z would equal the score we're interested in minus the mean divided by the standard deviation. So it would give us a z-score of -1. Go to table A, look up -1.0, which is 0.1587. -1.00 is 0.1587, which is approximately 16%, which is what we found from using the 68, 95, 99.7 rule. 0.1587, which is 15.87%. And guess what? If we went to the calculator, I wonder what we would get. Let me find the calculator. I lost that thing again. Let's clear out this calculator since we've got a bunch of stuff in there. Now again, second VARS distribution, I want normal CDF. We never use normal PDF. I want from negative infinity all the way up to 296. And again, his mean drive was 304, and the standard deviation of all of his drives was 8. 0.18 or 0.158655. When we did it using the 68, 95, 99.7 rule, we got about 16%, pretty close. When we did it using table A, we got 0.1587 or 15.87%, pretty close to the calculator. So they're all relatively close. You can do that problem any way you want. Okay, so we've looked at how to find the probability of greater than. We've looked at now how to find the probability of less than. What if we want to know the area in between two values? So for this problem, Jordan hits his driver. The distance the ball traveled can be modeled with a normal distribution. Mean 304, standard deviation of 8. Absolutely. Now, Spieth can drive the green in this problem if he hits the ball between 305 and 325. What percent of all of his drives would be in that interval? Is he likely to hit the green? Well, let's find out. Okay, so we're trying to answer this, the probability that he is greater than 305, but less than 325. So we want to know the proportion in between, which can be seen up here. We're looking for the area in between these two. All right, so we can find the z-score for both of these, which has been done up here. Find the z-score for 305, which is 0.13, and then find the z-score for 325, which is 2.63, and then find the area in between those two values on table A. So if we look at table A, and we're looking for 0.13, which is 0.5517, 2.63, which is 0.9957, and find the difference in those two areas. Because remember, this table is giving us the area all the way from the point we're looking at all the way back to negative infinity. So if I find the first area, less than 305, which would be this area. And then I find the area less than 325, which would be this area. I want the difference between the two, the distance between the two. So that's why we would subtract the area of 325 minus the area less than 305. Again, we could do this on the calculator as well. All we have to do is go to normal CDF, second VARS, normal CDF. Now I want to know the answer from between 305 and 325. My lower bound, 305. My upper bound, 325. My mean is still 304. My standard deviation is still 8. And paste it in and hit enter. So he has a 44.59% chance of hitting the green. That means 44.59% of all his drives would be between the distance of 305 and 325. Okay. Remember, all this z-score stuff only works if the data is normal. If the data is not normal, none of this is going to work. It all requires normal data. Okay. If the data is not normal, forget it. This will not work. You can only do z-scores for normal data. We're going to work backwards. What if we know somebody's percentile and we want to find out their score? Okay. So here's our favorite curve again. Let's say that we know that the heights of men in the United States is normal, with a mean of 67 and a standard deviation of 2.5. So that would mean a mean of 67 and a standard deviation of 2.5. So that'd be 69.5, 72, 74.5, and then so on over here. 64.5, 62, and 59.5. So I know that my buddy Montijo is at the 77th percentile, but I don't know how tall he is. But I know that he's taller than 77% of all of the males in the United States. So let's take a look at that. We're going to use our z-score formula to try to figure that out. If he's at the 77th percentile, oh, he has a z-score of 0.74. 77th percentile lies at a z-score of 0.74. So we can work backwards to answer this question. So remember, the data is normal, so it's z equals x minus mu over sigma. Well, I know his z-score is 0.74, but I don't know how tall he is. But I know the mean is 67 and the standard deviation is 2.5. So I'm simply going to solve this equation for x. Multiply both sides by 2.5. So I know the 70 percentile is going to be 77th percentile is going to be somewhere in here. So I'm looking for this area under the curve. 2.5 times 74. Let me get out my other calculator here. 1.85. So 1.85 equals x minus 67. Add 67 to both sides, and I can find out that Montijo is 68.85 inches tall. So that's how we would solve a problem working backwards. Okay. 68.85 inches tall at the 77th percentile. So Montijo is 5 foot 8.85 inches tall. That's how we work backwards. We find the z-score first by looking it up in table A for that percentile, and then we solve for x because we will know the mean and standard deviation. Okay. So how do we find less than? Use table A. How do we find greater than? 1 minus what we find in table A. How do we find in between two values? We find both values in table A and subtract the two. How do we work backwards? Use the percent to find the z-score and then solve for x. That's everything you'll need to know for the normal distribution.